All right, welcome, my three troopers. My son Nathan will be joining us, but he's not taking the class. He just wants to learn some. You could have either one of these textbooks. This is the second edition. This is the third edition. If I was you, I'd probably go with the second edition because it's going to be a lot cheaper, I'm sure. The textbook is a very standard textbook. We will not be using the textbook for homework problems for the simple reason that you can find the solution for every single one of those problems online. In fact, on the Moodle website, I have a link to the solutions to every problem. That's actually beneficial as you're preparing for the test. You can go through and you can practice doing problems and make sure you do it right. The explanations are very good on the one that I have linked. But it wouldn't be useful to assign those as homework problems because then you would have the tendency to just go through with that. The reason we're meeting Monday, Tuesday, Wednesday is because Aaron plans to be missing a lot of Thursdays and Fridays this semester. And so with only 3 people in the class, it's important that we're all here rather than one person getting left in the dust. And while I know you would have worked hard to stay up to date, it's just better to be able to have you here for class. With that said, if you're going to have to miss a class for any reason, please let me know as soon as possible, and we will simply reschedule the class. I don't want to have the class with one person missing. I want everyone to be able to be here. Even though I'm recording the lectures and will upload them, I got a comment on Sabbath, somebody saying, hey, good explanation, can you do this? So they will be there for you, but I want to make sure everybody's here so you can ask questions and whatnot. Notice my office hours are listed here. Those are times when you can come and ask me questions. Any other time that I happen to be in my office, students are my top priority. So if you have questions, you can come by and ask me questions. The objectives for the class are for you to understand quantum mechanics. Now, I know the 3 of you are all taking the chemistry version of this, right? And so for you, you have the kinematics, that's 1 lecture per week, and this is 3 lectures per week. If I was teaching it to physics students, I would actually have a 4th lecture a week. What we actually would do, what we did until we got to the point where we didn't have physics students taking it, is we just did with you chemistry people for about 2/3 of the year, and then you were done, and the physics people continued on. Our goal here will be to understand what quantum physics is about and to get through doing the hydrogen atom in a simple form so that you can understand this is the basis of what chemistry is based on. This is the fundamentals of chemistry. We had a quantum mechanics class that it's a little demeaning the way I say it, but it's still true, so I'm still telling you. We had a class that was labeled as a 400/500 level class. It was physics 450/550. 550 is a first-year graduate level. 450 is a senior level. And they made all of us graduate students take it because they said none of you are coming in with a sufficient understanding of quantum mechanics. So it was a remedial quantum class, and then we had 2 other quantum classes we had to take after we finished the remediation. Chemistry graduate students also had to take that class. And why do they have to take it? Because it is the fundamental of what chemistry is about. And they considered that their weed out class. If you could get through that quantum physics class, well, then you were going to get your PhD in chemistry. Whereas for us, it was remediation. And we thought that was hilarious as physics majors. But I'm telling you this not to demean chemistry. Chemistry is important and difficult, but to understand it really is, it's the fundamental basis of what chemistry is about. So I've talked about class attendance. We have some interesting things going on with the prerequisites, so we won't talk about that. Do please make sure your phones are on silent mode and you're not using the phones during class. If you can learn what we're doing and have your attention split between the phone, well, then you're really pretty good, because this isn't going to be simple stuff to comprehend. The math is hard, but it's bizarre. And so it's a lot of, wow, really, what, how? Ideas that are going to be going through your head. Please note the statement here on academic integrity. Make sure that when you do your homework, it is your homework. You didn't go online and find a solution and just copy that solution and so on. At the same time, I hope that you will get together and work as a team on the problems. Right? 2 heads are better than 1. In this case, 3.5 heads are better than 1. I say 3.5 because Nathan's actually not probably going to do the homework since he's not taking for grade. Work together, you can help each other understand better. I will share this story, a story of grace. When I was taking this class in college, I don't remember if it was the first or I think it was the first exam, but on an exam, I just made a mistake. And you know how these problems are. You make one mistake and it can end up being a big point thing. And I was just distraught because, I couldn't take that low test grade. And I went and talked to the teacher, and the teacher shared, I did not think that the teachers knew this. He said, I know that you're the only one in the class who understands this, and you've been working with your classmates to try to get them up to speed. And I'm not going to let my top pupil have a low grade because, of a simple mistake. And he actually let me just sit down in his office and redo that problem because, but the key here is working with your classmates, helping them understand will help you and will help them. So I really hope that you guys will work together. But make sure that in the end, you understand what you turn in, that it's your work and not just, Trey said do this and you said, well, okay, but that you understand it. So I do not at all consider it cheating for you to work together in your homework as long as you understand what you turned in. On the other hand, if it's on a test, different standard. The grade is pretty simple quizzes. Last time I taught this, I only ended up giving like 4 quizzes. The scores were really bad on them. I didn't count toward the grade because, the students were learning stuff, but weren't able to perform on the quizzes. I will try to have quizzes on a very regular basis. It's hard for me to do that. I just don't like quizzes. If there is a student who is absent, they didn't warn me, they just aren't here, then we will have a quiz. That's basically my way of, if you miss class, it's going to hurt. Unless you tell them we know what's going on. The homework is a big chunk of your grade. Like I said, the homework problems are not taken from the textbook. They will be given to you on Moodle. I kind of have the Moodle page going. Right now I have homework assignments there from the last time I taught it. So they all say Physics 412 because I taught it at Southern last year. So I may or may not change the Physics 412. I'm planning on using the same assignment. So it's just changing that number. So you can look there. The homework assignments are due on Moodle by 11:59 on the day shown. The first homework assignment is due Wednesday. It's only a single problem. But when I say only a single problem, it doesn't mean it's easy, okay? These problems, your hardest homework assignment might have 6 problems, and it's going to be a really hard week-long assignment. It's not, it's not something you should wait until the last day for them. Exams, we'll have midterm exams, which make up 45% of grade, and a final exam, cumulative final exam that makes up 20% of your grade. So 65% of the grade is from exams, 25% from the homework, and then that 10% from quizzes. I think we've covered everything I really need to cover. Do you have any questions? Oh, and there is no C-. It's a philosophical difference I have with Union College. To me, a C- is a passing grade. To Union College, it's not. And so I just don't give it, and that way I don't have to fight about it. You just get a C instead of a C-. Any questions? Yeah.
So since homeworks are due on Wednesday, does that mean that they'll be incorporating all of the lectures from Monday to Wednesday usually?
Yeah. From Wednesday to Monday.
Oh, okay.
Right. It's not going to be on the lecture that day.
Wait, but they're due, so it says that homework 1 is due this Wednesday.
Yeah, so it'll be just from today.
Okay. It won't be incorporating Tuesday and Wednesday's lectures.
No. In fact, I believe it's just from the first slide of the actual lecture part of the lecture.
Okay. And then I had one other question.
Sure.
Tests are going to be just 50 minutes long?
Yes.
Okay.
I went to get the book yesterday in the bookstore, and they gave me our thermodynamics textbook for the kinetics half.
Mm-hmm.
Do you know if they have the quantum mechanics?
They may or may not. I'm not sure. I didn't double check. Okay, before Christmas break, I started putting in the information. That's when I realized that there's a new version. And because we want to be in sync with Southern, I contacted them and asked them, are you changing to the new version? And I know I had started putting, I don't know if I finished, got an email in the middle of break saying, hey, what do you use for textbook? And then Ken responded, and then she responded, oh, I didn't realize you had it there, don't worry about it. So I assumed that I had finished it. I have to go back and check. I think we were only anticipating, well, where did you get yours in?
I got it on Amazon.
And you don't have one, right? So I'm guessing that they don't have them yet. I will talk to Terry just to find out, because I don't know. And like I said, it could be my fault. I know I started the process, but I may or may not have finished it. She sent an email saying don't worry about it, and so I didn't.
Are the homework problems out of the book?
No, that's like I said, all of the book's problems, you can find very well explained solutions online, which is beneficial to you, but I can't really use that as homework. All right. For some, I disabled the other thing, but yeah, I have a new version of Microsoft not working right. We've already talked about all of this. So here's our first slide. And like I said, I think that, oh, hey, well, come on now. You can wait until now to let me know? No, I had the syllabus going there. Yeah. Nice. By the way, the lectures will be recorded and uploaded to Moodle, so you can go back and peruse them as you'd like. So today we're going to start with the history of quantum mechanics and what it's about, how it came about, what we're trying to do. So in 1859, Gustav Kirchhoff, and if it's not 1859, we'll see in a moment, was the person who determined that if you get something hot, it will give off light. And that there is a relationship between the intensity of the light and the wavelength and the temperature. So yeah, 1859. Now, we don't have an equation for it here. We just have that there's a relationship. So that's our first understanding really of black body radiation. Now, with today's knowledge, we know that light is an electromagnetic wave. The electromagnetic waves are given off of anything that has a temperature. But this is the beginning of the quantum physics story. Now, something that is a little bit important, especially in quantum mechanics, so I bring it up now, is this thing right here. Oh, really? Yeah, had that problem this morning too, didn't we? Let me try. Close. Okay, the thing that I accidentally put the dash through. We have I, the intensity, is a function of wavelength and temperature, d lambda. What does d lambda mean? Okay, lambda is wavelength. D means an infinitesimal change. So what this is saying is the intensity at wavelength lambda and temperature T that you're going to have in some small width d lambda. That's an important concept, because if you think about it, let's say we have a light source, and I say, what is the intensity of light between 410 nanometers and 420 nanometers? Right? I have this range. I can easily measure how much comes in and determine my answer. Intensity is the power per unit area, by the way. Not really important to this, but that's what it is. Now, what if I say, okay, that was in the range from 410 to, 420? What if I want 410 to 401? Well, it's going to drop by 1/10, right? Because I'm going to have 1/10 the amount of light if it's consistent over all the wavelengths. And if I say, well, now I want from 410 to 410.00001, it's a much, much smaller intensity. And then if I say, what's the intensity at exactly 410 nanometers? No plus or minus. What do I get for that? It's going to be 0. Because if you have no width, you have nothing. you have to have a certain amount of width to actually have some light, because any light you have is going to be a little bit higher or a little bit lower than exactly this value. And so the reason we have the intensity d lambda is because we need some width. It can't be at a zero width. And so what we have is the intensity. The intensity is, once again, the energy per time, that's power, per unit area, per also the change in wavelength for a very small wavelength.
So you're saying there would be no waves of light exactly at 410 nanometers?
There would be, statistically, you would have a vanishingly small amount at exactly 410. If you had plus or minus 10 to the minus 27, sure, you would have something. But with plus or minus 0, it's on the order of 1 over infinity.
What about the temperature portion of it then? It's dependent on temperature as well. What if you had vanishingly small amount but it was very, very hot?
The measurement is going to be a measurement that is spread out. What you use, it's the form you're making the measurement. You're making the measurement by taking the light and spreading it out by wavelength and then choosing this piece. You're not taking the light and spreading it out by temperature and choosing the piece. So that's why it's d lambda. I had to think for a second. I was like, But yeah, there's a reason. So this is our beginning saying that, and does it seem like quantum mechanics at this point? No. But recognizing that we have light that varies by wavelength and for a given temperature. And this lower line, I can't underline anything, is the energy density. That is the energy per unit volume, is 4 times that function that Gustav Kirchhoff had come up with divided by the speed of light. The energy density is an important aspect that I will continue on this page. So we jump forward, that was 59, we go to 94. This is when most textbooks say that the photoelectric effect was discovered. Not by Wilhelm Wien here, but in this time frame. Wilhelm Wien was studying this black body radiation, and he determined that there is a very simple relationship between the wavelength that will have the longest light and the temperature of the object. This equation that's shown in the middle of the page is called Wien's law, and it says that the wavelength of highest emission is this number, 2.898 times 10 to the minus third meters times kelvins, divided by the temperature in kelvins. Now, one thing that I like to point out here, simply because it's an important mathematical concept and something you would have never guessed. If this is the peak wavelength, like the wavelength that has the peak emission, how could you determine the frequency that has the peak emission?
1 over Hertz C.
Yeah, close. Who knows where this is going to show up? I'm going to put it in the purple. We have the relationship that says, and I'm going to use nu because F is used elsewhere. Close enough. The frequency is speed of light divided by wavelength. That's the Greek letter nu for frequency, c for the speed of light, and the Greek letter lambda for wavelength. And so typically you would just say, well, I'm just going to use that relationship to calculate what the frequency is. And you would get the wrong answer. And this here is something that seems really peculiar. How is it that if I use that equation to compare or to relate wavelength and frequency, I don't have the same, or I don't have the right answer for the peak frequency? And the answer is, if you look at this bottom line, the energy density as a function of frequency, nu, and temperature is equal to the energy density as a function of wavelength lambda and temperature times d lambda d nu. This whole thing is because a change in wavelength of, let's say, 1 nanometer does not result in the same change in frequency as you go across the spectrum. Because of that inverse relation, when you're at a high frequency, you're going to have a much bigger DF for the same d lambda. And so you have to go through and put this correction in. So the basic idea is the size of your windows isn't the same when you have DF versus a d lambda. And so that's why the peaks don't correspond. Now, how do we understand this black body radiation? Lord Rayleigh went through some perfect physics. He said that the average energy per degree of freedom is kT. Remember, we talked about the equipartition theorem, saying that you have an energy. Now, when we were doing the equipartition theorem, it was 1/2 kT. It's slightly different here. We're not worried about why. At least I'm not. But you have the same amount of energy in every way that it can store energy. And so, saying that, then he said, well, the number of degrees of freedom for a standing wave in a cavity, and he just calculated based on geometry how many degrees of freedom you would have. And he put those together, and he said that you should have the energy density times d nu for low change in frequency is this function. But there's a problem, because what this says is the energy at some given frequency nu is proportional to the frequency squared. So if you go to high frequency, what's happening to the energy you're getting at that frequency? What happens if you plot u as a function of nu here? As nu goes up, what does u do? It goes up as a parabola, right? Well, that's problematic, because that says as your frequency goes toward infinity, the amount of energy at that frequency is approaching infinity. Which means no matter what the temperature is, you're giving off an infinite amount of energy per second. And if you're giving off an infinite amount of energy per second, either you're freezing or you have an infinite energy supply that's, right, it doesn't make sense. And so that's called the ultraviolet catastrophe. Ultraviolet because high frequencies correspond to ultraviolet light. Catastrophe because it was a catastrophic failure of physics theory. This is perfect physics, by the way. There's no flaw in it if classical physics was correct. And so that's where quantum mechanics comes in. Because classical physics, it turns out, wasn't correct. I mentioned in class, nope, different class. At the turn of the century, in the 1900s, scientists thought that they had everything figured out. Then you get something like this. So here's a graph showing the actual behavior. So this curve here is the actual behavior of the amount of light. Notice this is frequency here. So the amount of light emitted as a function of frequency. And this is what Rayleigh-Jones did it somewhere around as well. This is what their theory looks like. And it actually agrees really well at low frequencies, but at high frequencies, nothing alike. So now we enter Planck. So Max Planck was working on trying to understand this. And I do have the information here. He received a telegram telling him about low temperature behavior of black body radiation. And so he's like, whoa, if that's the case, then this equation should be correct. So given that last little bit of information about experimental results, he wrote down this equation, sent it off to the postcard that night. Which, I mean, that's sheer genius, okay? That's really good. But the problem is, he's got an extra term over there. The stuff outside the parentheses is a new term. And so as a physicist, why do you take physics? To understand how nature works. Well, he's got an equation that works. It gave a perfect fit. to this graph here. But he has no reason for it. And that's really unfulfilling. It's like if you write computer code, hey, my program works, but I don't understand. It should, it shouldn't as far as I can tell, but it does. And so then Planck sat down and tried to figure out, now, why am I correct? And over the course of the next months, he came up with a new and novel idea. I've got a typo there. Energies of Hn is not what it should be. But he determined that if the energy of light can only come in quantized steps. Now, in physics class today, we talked about electric charge. Electric charge is quantized. There's only certain values you can have. And he said if the energy that comes with light is only certain quantized values, in that equation where it says Hn, I'll never be able to fix this, but I'm still going to try. I'm going to try crossing out the LD. Nope. Well, then OU is going to do it. Cross out the OU and make that H nu n. All right. Okay. It should be H nu n. H nu n. Almost fit. Right over the word B, and I think it'll work. There we go. H is Planck's constant, nu is the frequency, and n is an integer, 0, 1, 2, 3, 4, 5. If for any frequency nu, your energy is h nu times an integer, then you have a different statistics, as we say in physics. When you're doing the equipartition theorem, you get a different result, and it adds in that additional term. And so he said, if we had quantized amounts of energy for light, then I can give you an explanation for why my equation is correct. Trace,
Could you say what H nu and N again?
Okay, H is the self-named Planck's constant. So H is just a constant, 6.626 times 10 minus 34 joules seconds. Nu is the frequency.
Okay.
And N is an integer, 1, 2, 3, 4, 5. So this is a quantum hypothesis. Quantum because he's saying if the energy can only have certain values instead of continuous range, then he could give us an explanation. So that's really the beginning of quantum physics right there. Einstein. So 1905, the advent of modern physics, Einstein wrote 3 papers that I am aware of. He could have written more. This is when Einstein was working as a patent clerk. It was a job that he considered ideal. He would be a man that today would be considered very ADD. Right? He couldn't focus on something at one time. He loved the patent clerk because people would bring in these ideas and he'd check to see if they worked and then he'd go on to something else. Not stay and work on one thing over and over forever and ever, which is the way science works. And then he and his buddies would get together in the evening, throw back a pint of ginger ale, I assume, and have fun talking about the day's scientific, topics. And so he wrote 3 papers, and those 3 papers, I will of course name the important one last. So the first one was on Brownian motion. You guys studied Brownian motion? I did back in high school biology. Brownian motion, the observation was that if you had pollen grains floating in water, you look out with the microscope, you saw the pollen grains doing some kind of little wiggly action, shaking about. And Brown's initial explanation was it must be some cavorting beasties, i.e. some microscopic life that is pushing on them to make them bounce around. But Einstein wrote a paper and said, no, it's not that. It's the kinetic nature of matter. That because that water is not at absolute 0 temperature, that means the water molecules are flying around in there. You don't see them flying around, but that pollen has such a low mass, which means it has such a low inertia, that the pollen is actually bouncing off of the water molecules that hit it. And so you're seeing the result of the moving water molecules. So that's one of his papers. Second paper, which is the one everybody thinks he's famous for, okay, so he is famous for, but is his on a special theory, or on a theory of special relativity. The third paper, the one for which he shared a Nobel Prize, was on photoelectric effect. And the photoelectric effect was his experiment to show that light really does come quantized, as Planck had suggested. Planck just hypothesized if the light comes with quantized energies, then I have a reason. And Einstein said, he's right, light comes in quantized energy. So he proposed an experiment, the photoelectric effect experiment, which had been, as we saw, first observation was like 1859. When Hertz was doing his experiments to verify Maxwell's proposition that light is an electromagnetic wave, he noticed that when you had ultraviolet light, the arcing occurred more easily. And so retroactively, people say, he observed the photoelectric effect. But what was known was that if you take an electron and you make an electron hit a surface, that surface is going to give off light. And if you have a hot surface, it's going to give off light. Did I say it right? It is kind of right, but the photoelectric effect is that when you have light hit a surface, it will kick off the electrons. That's what I'm going to say. You have light hit the surface, it'll kick off electrons. And so he said, okay, if we were to go with conventional wave theory says that I can shine my light with any energy. I can make it brighter and dimmer, and that's going to have more or less energy. And so if I make it brighter, then conventional theory says I'm putting in more energy, so I should be able to get electrons off of the surface that have a higher energy. Whereas if it's dimmer light, then I won't get as energetic of electrons off. But Einstein said, now, if Planck's idea is correct, that light comes in packets of energy, then if I make my light brighter, I'm just making more packets of energy hit. But an electron's only going to be hit statistically by one packet of energy. And so the energy that an electron has is just going to be the energy of that one packet. So it doesn't matter how bright the light is, the energy the electrons come off with will be the same. If I change the frequency, because Planck's relationship said that you had packets of h times nu, Planck's constant times the frequency, if I raise the frequency, then I should raise the energy electrons come off with. Then it's going to get more electrons with the same energies. And so he proposed this experiment. Now, one thing I really admire about Einstein, his intellect was amazing. As far as I know, he never did an experiment in his life. He proposed these experiments, and then, the answer is obvious. But people did do the experiment, and they found that Einstein was correct, that it didn't matter what the intensity of light was, the energy of the electrons only had to do with the frequency. And so now we have a confirmation that the radiation is quantized. Now, Einstein had initially said in this case, and then like a decade later, he wrote another paper and said, no, in every case, light comes quantized. Okay, it was 1887 when Heinrich Hertz observed that photoelectric effect. This is just going through what he observed. He didn't have anything in mind of what Einstein did, but retroactively say, he observed it. And then in 1915, we had the first experimental confirmation of the photoelectric effect experiment. Or now we do it in physics lab. It'll be like our next to last lab in physics will confirm it. 1916 is when Einstein reevaluated and said that really all light has these properties. And then 1923, Arthur Holly Compton, in writing his dissertation, and I think his dissertation was something like 22 pages long. What a day. My dissertation's more than 10 times that long, He said, based on what Einstein has come up with, we have in agreement that light is both a wave and a particle. Right? We know we can measure the wavelength. We have experiments that show the light behaves as a wave. That is, if you have light go through a diffraction grating, it'll separate out the colors. That can only occur if light's a wave. It can't occur if light's a particle. And yet we have the photoelectric effect and the Compton effect. Oh wait, this is Compton. I think Louis Broglie now instead of Compton. Compton effect comes before Louis Broglie. So Compton effect is actually looking at scattering of light. What Compton observed was if I have light hitting material and scattering, that when it scatters, he actually had light of one frequency comes in, light of two frequencies comes off. And classical physics says you can't do that. You can't change the frequency. But if you treat light as a particle that has energy, you slow it down, you lower the energy, and that changes the frequency since energy is h times frequency. And so Compton scattering was another observation that light has apparently a particle nature. So this is going the right direction. I'm not sure. Swipe it that way. And so this is the explanation of Compton's work using the relationship, both relativistic calculations actually, and the particle nature of light. So he's using two of Einstein's three papers here. He determined that for conservation of energy and momentum, you have to have a shift in wavelength for the particles, and it gave exactly the new wavelength, or frequency if you prefer, that he observed. So 1923, the same year, this is Louis de Broglie, the year we got shot. Louis de Broglie in his thesis said, if a photon, if a particle of light can also be a wave, then what's so special about light? Why can't, for instance, an electron be both a wave and a particle? We always think of electrons as particles. And so he said, why can't an electron be a wave? And he came up with a wavelength for the electron. The wavelength is Planck's constant divided by the momentum. Momentum, mass times velocity, as long as we're not relativistic. And so Louis de Broglie suggested this. Now, I'm not sure what I have. I don't want to go here. I want to stick with that idea. So I know I have papers that I posted on the Moodle site that deal with this. It's kind of interesting to me to look at the history here. Erwin Schrödinger gave a talk about this idea that de Broglie had come up with. And after he was done, another, and I can't remember which great mind, kind of dismissively said, well, if the electron's going to behave as a wave, then shouldn't there be a wave equation for it? And so Schrödinger's up, yes, there should. And Schrödinger sat down and he went through energy calculations and came up with a wave equation to describe the wave nature of an electron. And that equation, the Schrödinger equation, is going to be the basis for this class. So that's one of the two developments of quantum mechanics right there, going from Louis de Broglie's, hey, why can't an electron have a wave nature, to Schrödinger's wave equation. Now, these other experiments here are experiments that show the quantized behavior of electrons. So I'm going to go to the Davison-Germer experiment. What they did is they scattered, electrons scattered off a crystal, and electrons, as you probably know, have a spin, right? But what does spin mean?
I was watching a video about this last night. It's weird.
It's not what they thought it meant. They came up with the term spin because they noticed that electrons interacted with magnetic fields. And why would an electron interact with a magnetic field? Well, it would interact with the magnetic field if it has a magnetic moment of its own. And so they said, well, the electron has a magnetic moment. How can it have a magnetic moment? Well, that's easy. How does the Earth have a magnetic moment? The Earth has a magnetic moment, we believe, because we have this molten magma that's going around in circles. If you have charge going around in circles, it creates a magnetic moment. And so they said that must be what's going on with the electron. The electron must be spinning to give it a magnetic moment. Well, we now know that's not correct. We don't know the size of an electron. Some people propose that there is no volume to an electron, it has no size. Others say, no, it probably has some size. It doesn't seem likely to have no size. But we can calculate a maximum size of an electron. We know it's smaller, and I can't give you a number right now, but smaller than this. And the electron would have to be spinning so that the surface of the electron, if it was that small, was going faster than the speed of light to create its magnetic moment. In other words, it's not possible. It's simply not possible that the electron's magnetic moment, i.e. the electron spin, is a result of the electron spinning. So instead, we believe that electrons have an intrinsic, just a built-in, magnetic field, magnetic moment. And so when we talk about the spin, we're just talking about its intrinsic magnetic moment. And we're going to learn a lot more about the spin. But what they were doing is they said, okay, so we have these, boy, I sure hope this is the Davison-Germer experiments, like not the only people who ever did experiment. So we have these spins, and if the spins are like anything normal, then they should be able to point in any direction. And so if we put our beam through, I'm worried that this might be the wrong thing, because they were taking silver atoms and putting them through a magnetic field. And instead of seeing them interact with the magnetic field and have a continuous distribution, they found that they had only, I wonder if I have a picture of it. No, it doesn't look like it. Oh, there it is. Oh, it's Stern-Gerlach's the one I'm explaining. See, wrong people. They're silver atoms. Instead of having continuous range of angles for the spin, they had only two possible outcomes for the orientation of the spin, which you guys know is up and down, right? And like I said, we'll learn later more about what it means. But what they found is you only have two possible spin states. Okay, so let's go back now. So that was the wrong one. Yeah, these ones here are just showing that both of these are showing that electrons have effectively a wavelength, have a wave behavior. I'm sorry, I got the names Davison-Germer and Stern-Gerlach confused. And that's certainly the wrong direction. At this point, experiments have shown that electrons, protons, neutrons, hydrogen atoms, helium atoms, and fullerenes are all particles that have wave behavior. So why don't I see a wave behavior of Chad? Because he's so massive. Because he's so massive, the difference between his levels is so small that we can't discern them. We see it as continuous. So we don't see it quantized. So it's just because of your mass.
What's the last
one? Fullerene, okay, notice buckyballs. It's a buckyball is a specific fullerene that looks like a geodesic dome made of carbon atoms. So it's, you have graphite or you have diamond structure. This is another structure for carbon that's much more complicated. Okay, and yeah, that's I think the right way. Nope. This way. Okay. Now, we're switching gears now from the Schrödinger approach to the Heisenberg approach. Heisenberg and Schrödinger came up with quantum theories completely separately. And so we go to J.J. Thomson. He studied what happens when you have a cathode and anode. He found cathode rays, something went flying out of the cathode. And after some experimentation, it was determined that these were electrons. And that realization that there were electrons in matter then brought about the plum pudding model that said that if I have matter, I'm going to have basically a sludge of generally positive charge. And then I'm going to have like these little raisins that are electrons in it. So that's the plum pudding model that J.J. Thomson came up with because he knew that there had to be electrons in his cathode. And then we go to 1908, Geiger and Marsden. I intentionally dropped off the name Rutherford. The story to me is interesting. Rutherford was the head of the research lab. And Rutherford had working for him Geiger, who is reasonably famous. Everyone's heard of the Geiger-Muller counter, right? Often we just call it Geiger counter. Nobody's not heard of Muller, apparently. Marsden was the news. Marsden was like the new grad student. And after he'd been working for a while, Geiger goes to Rutherford and says, I think young Marsden here is ready to do his own experiment. And so Rutherford says, well, let's do a simple thing. We believe that matter is basically just this positive sludge with these little negative charges in it. So if we take gold, a malleable material, as you take it with a mallet and you smash it, it doesn't fracture, it just squishes. We can make really thin films of gold. And so let's take a thin film of gold and let's have Marsden shoot alpha particles at it. Alpha particles, at this point we know them as helium nuclei. What they knew then was, they knew these alpha particles are massive. And so what they expected was you have an alpha particle hit this film, it's going to hit that positive sludge, it's going to just slow down a tiny bit. If it hits an electron, maybe a tiny bit more. It might, if it comes close and doesn't hit an electron, it might deviate just a tiny, tiny fraction, but the electrons are so much less massive than the alpha particle, it's going to be virtually no deviation. So let's just check it to make sure that's what happens. And so Marsden does his experiment, and he finds that most of them go through with zero change. No change in velocity, no change in deviation. But some of them went bouncing in all kinds of crazy angles, including bouncing straight back. Now, it doesn't take a genius to know if I have a heavy ball and a light ball, and I have them bounce off of each other, the light ball is always going to be the one that has the big change, the heavy ball, virtually no change. And so if I have the alpha particle come bouncing straight back at me, that means it was bouncing off of the heavy ball. So, and so they realized right away that there is something clearly wrong with this plum pudding model, that there must be a massive thing in the gold foil. And so Rutherford came up with his planetary model, saying that an atom being a term that had been coined long ago, means indivisible, must consist of a nucleus that is very massive, and then electrons that are orbiting it, kind of like planets orbit a star. And very quickly, that was refuted. So if that was the case, you would have electrons doing circular orbits. Some of you might still think electrons do circular orbits. Not true, right? We don't know what paths they do. That's part of this, part of the reason for Heisenberg's quantum mechanics. But if an electron was orbiting the nucleus like a planet orbits the sun, it'd be doing circular orbit, and it's constantly accelerating, right? Changing direction is an acceleration. And our understanding of electricity and magnetism says that if I have a charge that's accelerating, it has to give off radiation. And so the electrons should be losing energy as they orbit, such that the electron should crash in the nucleus in less than a nanosecond. I.e., there would be no stable atom if the Rutherford model was correct. You would have just protons. Furthermore, the hydrogen emission spectrum, if I take hydrogen atoms and I excite them, they give off only specific colors. Well, our planets don't have only specific orbits. They can orbit any distance from the sun. And so they can have any energy. So those are two things that clearly were wrong about Rutherford's model. So Niels Bohr, came over and worked with Rutherford, and he proposed a quantum condition. He said, let us suppose that the angular momentum that an electron has as it orbits the nucleus is quantized. It can only have certain values. And so he said that the angular momentum must be an integer multiple of Planck's constant divided by 2 pi. Planck's constant divided by 2 pi is ubiquitous in quantum mechanics. Some people call it the reduced Planck's constant. Some people just call it Planck's constant. We have a way of writing it because it's used so much. And that is, I don't know why, that is, that was close. This is brutal not being able to write. Let me just write separately. Or not. I will get to the bottom of this. Okay, here. Erase. 8, too high. I should have not had the new version of Microsoft Office installed last night. Okay. We put H with a slant through the upstroke to mean Planck's constant divided by 2 pi. Oh man, I'm out of time. I haven't even gotten to Heisenberg's actual method. I will end by saying Heisenberg, realizing that they can't figure out what the path is an electron's taken as it orbits the nucleus, decided to give up on that. And said, let's categorize what we can know. So we can know what the energy is, and we can know what this is and that is. And so he started basically making matrices of the different properties of the electron and not worrying about what's going on. And he didn't know what to do with this. He took it to another person. He's like, I don't know, send it off to a mathematician. Mathematician, oh yeah, you're just doing matrix math here. And that gives us the second way that quantum mechanics was developed. All right. We'll meet again tomorrow.